Right, good morning science fans. We are pressed for time here and you'll see why in a minute. You're not going to see a lot of me, but what you are going to see is a lot of the science. Right, what are we talking here? Let's put a heading up here first. We're talking about the escape velocity and terminal velocities of any object, right? That is not meant for down there and that just for there. It's two things that we're talking about, right? Two things that we're talking about. Now, the escape velocity of a planet or let's say of the moon, it doesn't matter what it is a speed that you need to reach in a space vehicle to escape the gravitational pull of a planet. The moon's is 5,320 miles an hour, which is 8,560 k's an hour. Earth, it's 25,030 miles an hour, which is 40,284 k's an hour. The reason why it's more on Earth is because it's bigger, there's stronger gravity. Right, this rocket here, if it wanted to escape Earth's gravitational pull, when it takes off, right, it needs to reach at least 25,031 miles an hour. I don't know what would happen if it was 25 and 30. I mean, look, it doesn't matter, we're not going there. It would have to reach 25,031 or more miles an hour, because then as it accelerated up, it would get to the stage, doesn't matter how close it would be going 1 mile an hour faster than Earth is pulling it back. So it would get to the stage somewhere right up in the heavens where it would escape Earth's gravitational pull. It would just keep going, all right? If it was going at only 25,029 miles an hour, it would get to a stage somewhere, right? It's going up, but Earth's pull is a little tiny bit stronger. So the rocket would eventually get to a stage where it would just stop and listen, Earth would bring her back home and fast at 25,030 miles an hour. That's how fast it would come back. On the moon, right? So that's the command capsule, like on re-entry. So again, when this came back from the moon, it was in the vacuum of space. The speed that it would have reached is 25,030 miles an hour, because that's the force, that's the power of the gravitational pull that planet Earth has on all objects anywhere. That is how fast Earth is going to pull them back until they reach Earth's atmosphere. As soon as something reaches Earth's atmosphere, it's when it heats up, it burns up. That's why we see the meteors, asteroids, and that's why these command capsules have the heat shield, because when it hits the atmosphere slows it down, okay? Terminal velocity, right? Now we're talking terminal velocity. Terminal velocity on Earth, right? If you've got a parachuter or somebody falls out of a plane or any of these things, right? What happens is, so this is land, this is Earth, right? That little box. Somebody's chute doesn't open, right? My chute's not opening. Just jumped out of the plane, 10,000 feet. What happens? He will accelerate 9.8 meters a second acceleration. And terminal velocity, Alexa, what is terminal velocity for planet Earth?
Here's something I found on the web. According to Wikipedia.org, in stable, belly to Earth position, terminal velocity is about 200 kilometers per hour,
Okay.
120 miles per hour.
Okay, thank you. Right, so what would happen? No chute, no open, come out of the plane, you accelerate, but you only get to 200 k's an hour, because the atmosphere is slowing you down. So it's kind of braking you. You're still going to hurt yourself, die probably in most cases, but the atmosphere will only allow you to get to approximately 200 kilometers an hour. Those guys in the wingsuits, if they put themselves like this and they make themselves into like an arrow as they're going down, they reach higher speeds, maybe 250, 300, I don't know what it is, but because there's less resistance, right, they go faster, right? That is terminal velocity. It's a speed where you cannot go any faster, free falling, because the atmosphere is slowing you down. Now, let's go over to the moon. On the moon, there is no terminal velocity. So we scrub this out, right? It doesn't exist. Why doesn't it exist? Because it's a vacuum, right? There is zero resistance. Therefore, there is no terminal velocity to be spoken about. Now, to escape the moon's gravitational pull, it's a lot smaller. You only need to reach 5,320 miles an hour. That's 8,560 kilometers an hour. If you took off from the moon, this rocket took off from the moon, here, right, and it reached 5,319 miles an hour, the same deal as over here. It's going to take off and it's going to get to the stage where, listen, if that's all the power you've got, the gravitational pull of the planet is going to bring you back down. Smack. Now, this is where it gets, it's not complicated if you can grasp the concept. Let's talk about this parachute up, right? Now, if this parachute is on the moon, so now this isn't planet Earth, this is the moon, right? He falls out of the plane and he starts to accelerate. He pulls his chute open. Even if his chute did open, well, it wouldn't go because there's no atmosphere. But there is nothing to slow him down. So he accelerates and he accelerates and he accelerates until he gets to 5,320 miles an hour. Now, how long would it take to accelerate to that speed? I don't know, I never thought of looking it up. Maybe a couple of Ks, 3, 4, 5 Ks, I don't know. But the moon is pulling at him. And there's never any resistance to slow him down. So the moon is just coming at him like this. And thwanker, that's a nice word, right? He smacks into the moon because there is no atmosphere to slow him down. We know that's the moon because look, there's the cow that's jumping over it, all right? So we've got on Earth, 25,000 and just over to escape. On the moon, it's 5,320 plus to escape. On the way back down, the atmosphere causes a burn up, or if you're in the atmosphere already, you have a terminal velocity. On the moon, there is no such thing as terminal velocity because there is nothing that is going to slow you down. Okay, now let's go to part 2. We really are under the pump for time here. You will find out in not too long. That's if it lasts. Right, so hello, can you go? Hello, can you go? Greece. Right. Now, what we have here, 3 stacks of coins. Alright? It's a demonstration of 1/6 of Earth's gravity on the moon. This is a 5-cent coin. Here are 6 5-cent coins. So a human being, or even these coins on the moon, would fall like this, right? No, sorry, on Earth, I'm sorry. The weight, this is the weight on Earth, right? This is the weight on Earth. Now you see, it's still pretty hard, isn't it? Okay? It doesn't go any slower. This is 1/6 of Earth's gravity, right? They both fall the same, but there's no resistance, right? Now, they say if you drop two items, doesn't matter what they are, they fall the same speed on planet Earth. That is not true, because if you drop a feather and these coins, what's going to happen? The coins are going to drop and the feather's going to go like this, right? So it's slower. So this is the next setup. 2 5-cent coins, 12 5-cent coins. So what happens? If this, look, it's planet Earth, look. They fall the same, don't they? Right? Now these are 10-cent coins. We've got 4, there's 24, right? So this is the weight that we are on planet Earth. On the moon, you're 1/6 of that weight, that's 4 coins. But what we know is that they still here, because look, it's happening right in front of you. They fall exactly the same. If we go to the moon, there is no resistance on the moon. So if we did this, right, but with a feather, what happens? So we've got 24 coins, and we've got a feather, right? If we do that here, this is what happens. Because that is what happens. It's the air resistance that slows it down. If we were on the moon, feather, this pack of coins, there's less of a gravitational pull, so we're not getting pulled as hard, but there is no resistance. So if we drop into the moon from a couple of kilometers up, we are going to accelerate. Both of us are going to accelerate at exactly the same rate, right? What happens is this, right? It's not a case of in the vacuum we travel like the feather, right? That's not how it works. The coins remain the same. Boom! In the atmosphere, slow because there's air resistance. On the moon, there is no air resistance, there's nothing to slow this down. Both things drop at the same rate. Bang! Important. Now, this is it. This is now the final part of the experiment. It's held now. I will cry if this goes now. You still don't know what I'm talking about. So what we have, see, this is the real science. Look at this. There's 3 bricks on the left-hand side, right? There's a leaf in the middle. We could call that a feather. And on the right-hand side, there's half a brick. Okay, so there's 3 bricks and a half a brick. So that would be the weight on Earth. That would be your weight on the moon, or the weight, the equivalent on the moon, because it's 1/6. And then we have a leaf. Call it a feather, but it's a leaf. So let's just leave it a leaf. We don't need to pretend it's a feather. We're doing enough pretending here. But you're used to that as well, aren't you? So, just joking. Now, we are on the moon. All right? What we're going to do is cut this line. Now, the way I've structured it, this leaf is on a stick that runs over to this, and it's underneath that little bracket. Oh! Oh! Now, what we have to hope, I was going to put it on slow-mo. All we can hope is that there was a demonstration of how, see, that's science, isn't it? That is science. On the moon, I'm hoping that it all fell at the same speed. The leaf, the 2 bricks, because that's what would have happened. There is no resistance. things would accelerate to 8,560 k's an hour. So the Eagle, for example, because there is no resistance whatsoever, it is always thrusting, always thrusting. Now, thrusting into a vacuum from 112 kilometers when there is no resistance and you've got to slow that thing down, how? All right? Now, this isn't about that. This is about understanding that everything falls at the same rate, and it doesn't fall at the speed of the feather, it falls at the speed of the bricks, because there is no resistance for the feather. That is my point. So I was going to do the rest of Galileo today, right? But I started reading, and this is what I came across, so I had to address it. Because they make it sound like everything slows down to the speed of the feather, but it doesn't. The feather accelerates to the speed of the bricks because there is no resistance. All right, we'll be back with more. God, I hope that came out good.